Good morning, everyone. Thank you for joining this webinar, which is the final part of our computer vision webinar series. This webinar is titled Real-World Applications of Condition Monitoring Through Thermal Cameras and Vibrational Analysis, delivered to you by our presenter, Enzo du Plessis. My colleagues Varushan Kapoor and Doron Joff have delivered the first two webinars splendidly in the weeks gone by. Seeing that this webinar is the finale, I gracefully hope that this won't feel like the final season of Game of Thrones. If you know, you know. Anyway, let's hop into some housekeeping rules for this webinar. So for the housekeeping duties, ladies and gentlemen, please put your microphones on mute during the webinar, and this will enable that people don't distract the webinar. Secondly, the webinar will be recorded for those that cannot attend or would like to rewatch it. And then thirdly, if you have any questions or comments, please feel free to place them in the chat. They will be addressed at the end. Okay, so now that we're all good on housekeeping duties, let me share a bit of information about myself. So my name is Enzo du Plessis. I'm a junior consultant at Opti-Num Solutions. I joined Opti-Num Solutions as a grad as part of the 2023 graduate program. I studied mechanical engineering at the University of the Witwatersrand, and I'm passionate and curious about many things computer vision related. And so speaking about Opti-Num Solutions, here's a little bit about us as a company. So we are a data analytics, modeling, and simulation company who partner with our clients to develop data-driven solutions to complex problems. So we are essentially the sole authorized resellers of math. Of our clients you may recognize in the top right-hand corner, which are the likes of MTN, CSIR, and Anglo American. Our clients and the work we do spans many industries, which you can see in the bottom right-hand corner, which include business analytics, financial engineering, mining and manufacturing, digital engineering, as well as the research, teaching and learning, or the education space. So let's get on to today's agenda for this webinar. So on the agenda for today, we will delve into the following topics. We will look at anomaly detection in equipment, specifically in the mining and manufacturing space, as well as what the importance thereof, what the importance of anomaly detection. We'll also dive into concepts related to predictive maintenance. We'll look into a case study that is related to condition monitoring using thermal cameras in equipment. We'll go through a demo, which is related to vibrational analysis, and then thereafter we'll be doing a summary or a recap, and then at the end we'll have a question and answer session for a few minutes at the end. So, ladies and gentlemen, with all that said and done, let's dive into today's content. So, in the field of data science, where you have a large pool of data and you begin conducting some data analysis, you will notice that some data points are widely different to the rest of the data. Now, these data points are referred to as anomalies. So I'm sure that most of us essentially have heard about anomalies in data. So these are also referred to as outliers due to their far relationship with the rest of the data. So when companies gather data on their industrial equipment, they are quite intrigued by the anomalous data points appearing in the data set. Now, the age-old question to be answered is, why do companies care so much about anomaly detection for industrial processes and machinery? There can be a multitude of reasons for this, but the more common ones are in the first picture, to monitor industrial or manufacturing processes. And this is to improve the availability of assets for the company, as well as monitor and improve energy usage during manufacturing or mining operations, and as well as to manage their resource inventory. Now, the second reason is to improve product quality. Now, this is done by implementing strategies to diagnose and inspect defects on production lines and to optimize the amount of product that they have available. And then the third reason is to implement a maintenance strategy by scheduling regular equipment maintenance, which we all know to be very important in decreasing downtime of equipment operation and to also predict faults in operating equipment. Well, then we get into the question of how do anomalies impact the performance of industrial equipment? Now, anomalies are simply recorded equipment behavior that's picked up that deviates essentially from normal equipment performance. Now, data retains the top spot in ways to pick up anomalies, and typically the processing of data through some means is how we can pick up on these types of anomalies, provided that your company has systems in place to do so. Now, the current slide that you can see shows different anomalies that are picked up in signals and images. So I'm going to put my pointer on. So you can see in the first example, point anomalies can be easier to spot, such as outliers. And these typically are data points that differ from the rest of the data. You can also see for collective anomalies are possibly across many signals. And these anomalies may only appear when we look at a large group of data at once. You will see this in the demo that's planned for later in this webinar. And then we have visual anomalies found in images, can be picked up by using image processing techniques or deep learning algorithms. Now, as alluded to on the previous slide, some anomalies can be quite difficult to identify. Now, take, for instance, the time series plots on the left. By merely looking at these images, it's quite difficult to see any type of difference along these signals. However, when we transform the time series signal plots to the frequency domain, as can be seen on the right, it becomes easier to see the differences in peaks and hence spot anomalies. So you can see that there's a peak over here, and there could be a chance that they are anomalous data points. Now, what would make things easier sometimes is essentially to switch between the time series and the frequency domain plots. At least it would in this case. Now, for more resources on anomaly detection in industry, I highly recommend watching the first webinar of the Computer Vision webinar series on the 16th of August, delivered by my colleague Varushan Kapoor. Now that we understand a little bit more about anomalies, how do we then go about detecting them? Well, the answer to that is to have a maintenance plan or strategy for your industrial equipment. So when looking at what maintenance plan or strategy to carry out at your plant or operations facility, you would need to understand the different types of maintenance strategies. Now, in the main, there are three different types of maintenance strategies used by companies. Now, you can see the first one is reactive maintenance. And this type of maintenance plan involves only conducting maintenance once there is a clear problem or if there's an equipment failure. Now, the problem with the strategy is that it can be quite costly to repair the unexpected failures, and there is a danger element to this as well. Now, this danger element could apply in sectors such as the energy sector, the nuclear sector, as well as the mining sectors, where implementing this type of strategy could have serious implications if a critical equipment part fails within some of those sectors. Now, the second type of maintenance strategy is scheduled maintenance. Now, this involves conducting maintenance at regular intervals. This is a more common maintenance strategy implemented by corporations and does help to keep equipment parts in a healthy working state. Now, the problem with scheduled maintenance is that unnecessary maintenance can be wasteful in terms of cost and resources, and also it may not eliminate all potential failures within the equipment. Now, the third type of is predictive maintenance. Now, this involves forecasting when problems will arise by gathering data and performing analysis on that data using an algorithm, essentially. Now, this maintenance strategy identifies the optimal time to conduct maintenance in such a way that it saves costs and resources. Now, there is, however, a downside to this maintenance strategy, and that is that it is quite difficult to make accurate forecasts for very complex types of equipment. Now, on the bright side, predictive maintenance on equipment has proven to be a more superior maintenance strategy to implement, as it actively identifies anomalies in data and predicts when whether maintenance should be scheduled or not. Now, predictive maintenance can be broken down further into condition monitoring, where specific equipment conditions are analyzed, such as, for example, temperature or vibration, which we will go into later in this webinar. Now, staying on predictive maintenance, let's look at the predictive maintenance algorithm. Now, the predictive maintenance algorithm helps make maintenance decisions based on large volumes of complex data. Now, data is fed into the algorithm as an input, while the middle layers essentially are where the algorithm performs its analysis. Now, it identifies specific features in data to deliver a prediction on the health state of the equipment. And as well, depending on the complexity of the algorithm devised and trained, the algorithm will be able to make an accurate prediction as it takes a decision on the state of the equipment. Now, heading into the predictive maintenance workflow, how does this sort of look like? Now, the full predictive maintenance workflow is more than just an algorithm development. Now, the steps that I will go through entail obtaining data from sensors or synthesizing it by simulating system models. You pre-process the data and then extract the features to act as equipment health indicators. And these health indicators are used for condition monitoring and fault isolation. Now, the health indicators can also be used as inputs to predictive models that you can see over here, and are used to estimate the remaining useful life of the equipment and time to failure, for example, and as well as other metrics. And then lastly, this algorithm can then be deployed onto the cloud or on embedded devices. Now, with the above knowledge that I've shared with you guys, we will now delve into a real-world application of condition monitoring using thermal cameras. Now, this case study was derived from a research article published in the Institution of Engineering and Technology back in 2017 by Paul, Mayer, Menon, and as well as others. Now, to provide you with some context, they examined whether advanced protection techniques could be developed to predict whether when equipment of the existing power grid in India at transmission and distribution level would break down in an attempt to improve its reliability. Now, they proposed an algorithm for the real-time condition monitoring of substation equipment using thermal images obtained by thermal cameras. And I'll go into that in the subsequent slides. Now, the image in the current slide shows the block diagram of a substation monitoring system. Now, the diagram shows a 110/11 kilovolt distribution substation in which 4 on-site thermal cameras have been installed at 4 corners. And I can show with my pointer, the 4 cameras are over there, there, over there, and over here. Now, for additional information, the thermal cameras are capable of rotating both in the horizontal and vertical plane, as well as 360 degrees about its center. Now, the images are processed at the remote terminal unit, which you can see by this blue box over here. And the images that are processed there are extracted. They extract the speeded up robust features or SURF feature technique by passing them through 2 main classifiers. And this is the support vector machine or SVM, as well as the adaptive neuro fuzzy inference system or ANFIS. Now, applying this proposed algorithm at the remote terminal unit, the speeded up robust features are extracted from each of the images that are passed into it, and a critical fault condition is identified whenever the pixel intensity that you're measuring from the image that has been scanned is higher than what the threshold temperature is, which you can set by yourself. And this threshold value essentially is selected as per industrial standards. Now, the information regarding the condition of such equipment afterwards is sent to the substation monitoring control center, which is this orange block over here. And that, after it's been sent there, it will then notify the operators or people in charge for appropriate actions to be taken. Now, with that discussed, let's look at, let's take a deeper dive into what the algorithm for condition monitoring of the substation equipment looked like, proposed by the guys in this research article. Now, the internal working of this algorithm used in this paper is detailed in the flowchart, which I will show you just now. And each thermal image that is sent to the classifier will undergo this process. Now, step one would be to capture both the thermal and normal or RGB color images. Step two is to apply optical character recognition method to find what the maximum and minimum temperatures are in the image captured. The optical character recognition function is a function that is used where if you're feeding in data from whether it's an image or writing, that it's processed and passed into the language that the machine that's analyzing it can understand. Now, step three would be to compute what the row-wise and column-wise pixel intensities are. Thereafter, the algorithm will then compare what the intensity is, the temperature intensity is, versus the threshold temperature intensity. Step four would be to convert the pixels that have temperature intensities that are greater than the threshold temperature to white, while converting the remaining ones to black. And this is done to distinguish between equipment parts that have a temperature reading that is higher than the threshold value. The fifth step would be to apply median filtering and erosion technique to obtain what the presumable fault regions are, and these will be bounded by rectangular boxes. The sixth step is to crop these images based on the boxes and extract the speeded up robust features mentioned earlier of the cropped images. The seventh step would be to process the extracted SURF features through a trained support vector machine or an adaptive neuro fuzzy inference system or ANFIS classifiers to then distinguish between the critical fault and the minute fault conditions. And then the eighth step would be to mark what the critical fault detections with red boxes on the thermal images. And then what you would do is you would overlap them onto the RGB color images. Thereafter, this information regarding the health state of the equipment from what you're analyzing through the thermal camera will then be sent to the substation monitoring control center for then appropriate actions to be taken. Then if there's no fault detected or there's only a minute fault detected, the process is then iterated from step one and new images are passed through. Now, let's have a look at the results of this research article. What you can see on the screen are the results. And you can see in the first image, this is a thermal image having yellow boxes that we've placed on there for those equipment parts to be analyzed essentially. So we've got 1, 2, 3, and then this is a bit less visible, but there's a fourth and a fifth block or box rather as well. Now in the second image, you can see what the temperature rating is, or what the classification is after the thermal image has been passed through the classifiers. And you can see for the equipment parts here above, red boxes have been indicated on them, while green boxes have been indicated here at the bottom. The red boxes, as alluded to previously, would then identify these specific equipment parts as being faulty, while the green ones are ones that are not faulty. Then in the third image, image C, shows the RGB image, color image showing what the critical fault condition is with these red boxes, as well as the non-fault conditions with the green box. And this specific image has been passed through the support vector machine classifier. Now, with the content that I've discussed with you guys, we will now go into a demo where we'll be using vibrational data and we'll be trying to perform anomaly detection in industrial machinery using these 3-axis vibration data. So I'm quickly going to open up MATLAB. I'm just going to duplicate my display just for... Okay. Now, for this demo entitled the Anomaly Detection in Industrial Machinery Using 3-Axis Vibration Data, we'll be going through the purpose as well as the data that has been collected, as well as steps that we'll be undergoing throughout this demo. So what is the purpose of this demo? Now, this example, which you can find on the MathWorks site, which will be shared with you guys after the webinar, shows how to detect anomalies in vibration data using machine learning and deep learning. The data that we have is vibration data from a specific industrial machine, and these are the steps that we'll undergo. Now, firstly, we'll extract features from the raw measurements corresponding to normal operation using a MATLAB built-in app called the Diagnostic Feature Designer app. Secondly, we'll use the selected features that we've generated from the Diagnostic Feature Designer app to train 3 different models, and this is the one-class support vector machine, the isolation forest, as well as the LSTM autoencoder for anomaly detection. Thirdly, we will use each trained model to identify whether the machine is operating normally, and we'll also be comparing these 3 models against each other just to see which one performs better than the other. Now, for the data set, as I've mentioned before, it's 3-axis vibration data for an industrial machine. Now, I'll also go into how this data is collected. Now, the data is collected immediately before and after maintenance is scheduled. Secondly, the data collected after the scheduled maintenance, we will assume to represent normal operating conditions for the machine. And this is also the data that we'll be using to train the 3 different models that we have. Thirdly, the data from before maintenance, we can say that that includes either normal or anomalous conditions. And then fourthly, the data for each axis is stored in a separate column, which I'll show you guys just now. Now, what we can do in the live editor window, I've just enlarged it. Now we can download the data set from MathWorks. We can save it, unzip it, and then load it into MATLAB. I've already done that for us so we don't have to do that. But let's have a look at how the trained data looks like. So here you can see the trained data for each specific channel. And as I've mentioned before, each channel represents vibration measurements for each specific axis, as well as the label that indicates whether the data that has been gathered is before or after maintenance. Now, we'll try and understand the data set better by visualizing how the data looks before and after maintenance. Now, we'll be doing this by selecting the 4th ensemble member of the data set and plotting its vibration data. Now, the 4th ensemble will be the 4th row. We'll be selecting the data from all 3 channels for before, as well as the 4th row for after maintenance for that specific data set. Now, let's have a look at how that looks. We're also just using the helper plot vibration data function. We were passing in the trained data as well as the ensemble member. Okay, there's a quick error. Let me just have a look at that. It's also very important for all of your scripts to be added to the MATLAB path. Otherwise, MATLAB won't know where to find it. So let's enlarge that. There we go. So let me enlarge this figure. Now here we can see the vibration data for each specific observation, which is just the number of data points that we've collected. And we can see for each specific channel that there is a representation of the data, blue representing the data before maintenance was conducted, while red is the data for after maintenance was conducted. Now, you can see a bit of a pattern with all three of these graphs. However, this does not tell us much about anomaly detections or how this how the data looks between before and after maintenance, because by just looking at it, you can't really derive any meaningful insight. And that's where we're going to be going deeper into the data, and we'll be analyzing it a bit more. Now let's go into that. Now, the first thing we'll do is we'll be extracting features with the Diagnostic Feature Designer app, and I'll show you how to do that quickly. Now, from the features that have been generated, we'll be creating a function, exporting it, and saving it with the name generate features. And we'll also, in this specific example, extract the top 4 relevant features from each channel, of which there are 3, in the entire data set from the command line. So let me do that for you guys quickly. Now, to open up the Diagnostic Feature Designer app, you just type in Diagnostic Feature Designer. Now, a window will pop up. And what we'll do is under the Feature Designer tab in the tool strip, we'll click on New Session, and we'll be loading in the trained data that the tabulated trained data that I've showed you. Another window will pop up. So under the Select Dataset from Workspace pane, for the source of the data, we'll be selecting the trained data. And then that will populate information for each specific channel, which is channel 1, channel 2, and channel 3. What you can now do is to head to label, and then under variable type, select condition variable. And this will then indicate for each specific channel whether the data is for before or after maintenance. Now, once we've done that, we can click on import, and it'll just import the data into that. Okay, so now that we've done that, let's go ahead and generate some features. Now, for the first channel, what you can now do is generate features. You can head to the feature generation section under time domain features, click on that, and then select signal features, which will then compute the basic, will select basic statistical features that you can then select to generate features. So we'll go ahead and do that. Cool, so it's generated some time domain features for us, but it's selected all these features. Now you have statistical features, a statistical feature section, impulsive, as well as harmonic features. Now for this specific MathWorks example, for the first channel, we will be selecting 4 top ranked features, which will be the crest factor, the kurtosis, the RMS, as well as the standard deviation. So we can go ahead and deselect all the others. And this is just mainly for illustration purposes. And then after that, under the close section, you can just click on apply. And this will then generate a histogram of all those 4 features with probability on the y-axis as well as the number of observations on the x-axis. Now here you can see for each feature, it's generated a histogram with the labels for the feature values for after maintenance as well as for before maintenance. Now you can go ahead and do the same for channel 2 as well as channel 3. And you can select different types of features that you would like to implement. Just remember though, with different feature selections or combinations of features that you use, that will then have an impact on the training of your the models that you'll be using, as well as the results thereafter. Now, once you've done that for each channel, you will also see that there's a feature table list that gets generated that indicates each feature. And once you've done this for all 3 channels, you can click on, under the export section, you can click on the drop-down that says export, as well as clicking on generate function for features, and it'll just generate that function for you. Now, I currently already have done this whole process for us, so we'll just be having a look at what that function looks like. And the function is over here. Also ensure that you save it within the MATLAB path. So I've got this whole current folder selected on the path, and the generate features function is right there. Now, for the generate features function, you can see that it's generated a function for each specific feature, and it has included that with the output ensemble that we'll be using, reading one member, as well as obtaining all the input variables that we'll be using as well. So we can now go ahead and move back to the workflow. And let's have a look at what those features look like that we've trained. So here it has generated for before and after maintenance for each ensemble member, of which there are 40 feature values for each specific feature. So we've had about 12, 4 for each channel. Now, the set that I've showed you is only a small set of a much larger data set that was just supposed to illustrate the process of feature extraction and selection. Now, we're going to be training our algorithms on all the available data. So what we're going to be doing now is we're going to be loading in the same 12 features, but for a much larger data set of about 17,600 signals. And this is called feature entire, which is a mat file that I've saved. So we can go ahead and load this and have a look at that. So here we've got the feature values for each single ensemble member that is a little bit different to the feature value table that I've created before, and this is just because it's a much larger data set. Now, let's go ahead and split the training and testing data set using the CV partition function. And you can also use the helper extract label data helper function to find all the features that are of the label after, so that we are able to send all those data points to training the model. Now, we've used a 90-10 split of the training and testing data, and main reason is because we've got a large enough data set so we can dedicate more data points to training. So let's go ahead and do that split. Now what we're going to be heading into now is we're going to be training our model on the maintenance data that has been obtained for, on data that has been obtained for after maintenance. Now, we said that this we can assume to be normal, and we'll only be extracting this data from the feature train variable that I've created here. So let's go ahead and do that. And we'll be calling that feature normal. For this, you can now see for all the data points, we've got for the label after. So we'll just be sending this through our for training to our model. Now let's go ahead and detect anomalies using the one class support vector machine. This is quite a powerful classifier. The variant that I've selected for this demo today trains on only the normal data. So we'll be using this here. Now, this model works pretty well in identifying abnormalities that are quite far away from the normal data. So we'll be using the fit CSVM function to train this support vector machine model on data that's for normal conditions. So we can go ahead and do that. Now let's go ahead and validate the trained support vector machine model against the test data. And remember, for the test data, this contains both the normal and anomalous data points. So let's see how this model performs. Okay, so it performed pretty well. So we can see for the class that it predicted as the data points as anomalous, the true class was indeed anomalous was about 99.7%. Now this is pretty good. For the class that it's predicted as normal, the true class that was indeed normal, the prediction of that was about 99.1%. Now this did pretty well. However, let us go into using a different type of trained model to see how that performs as well. Now we'll be using the isolation forest, and this will then isolate each observation essentially into a leaf, and how many decisions for the sample that passes through to get to its leaf is then also a measure of how difficult isolating it is from the rest of the others. Now let's go ahead and train this isolation forest model on the normal data. Thereafter, similar to the one class SVM, let's go ahead and validate this model against the test data. And let's display its results on a confusion matrix. Now here we can see for the isolation forest model, it didn't perform as well as the support vector machine. However, we can still see that it performed pretty well with the data that it predicted as anomalous. The true class was indeed anomalous was about 93.1%. And for the class that it predicted as normal, for that true class that was indeed normal was about 91.3%, which is also pretty good. But now let's go into using what is called an LSTM autoencoder network. And let's see how that performs. Now, this is a type of neural network that learns a compressed representation of unlabeled data. So what we'll be doing here is for the training data that will be passing through to it, we'll be cutting off the label that says whether it's before or after maintenance, and we'll see how that performs. Now, because for this specific model, it will take quite a bit of time to train. However, in the workspace, I've got it pre-trained, so we don't have to run these commands. But you can have a look at this in your own time as well, where you construct the autoencoder network, set the training properties, set the number of epochs as well, and then you can go ahead and train it. It did take, especially with the computer that I used, it took about an hour to train, but it's already been pre-trained. So let's go ahead and look at how it performs on the validation data. And here we'll be taking a sample for both the anomalous and the normal conditions. And let's see what the decoded signal is that it plots. Okay, so for the normal input, when we tried looking at how the model performs against normal data, you can see the feature value indicated over here, the reconstruction error on the right, which will then give rise to these for each specific feature extraction that we've done previously using the Diagnostic Feature Designer app. So there were 12 features. This performed pretty well. However, for the abnormal input, now when we pass it a sample that has anomalous data, we can see that for some of the features, that there is quite a bit of a reconstruction error, which may indicate that there is anomalous data that has been passed in. And yeah, that was the result. But now let us go ahead and look at what for data that we're looking at for about 622 observations, let us go ahead and use this autoencoder model to see how it performs versus the in relation to the reconstruction error for both before and after the maintenance data. So we can have a look at that. Let me just enlarge this quickly. Okay, so before maintenance, the autoencoder network has a reconstruction error, an RMS mean error of about 3.94, which indicates that there are anomalous data points that are included within the sets that it has evaluated. However, for after maintenance, you can already see the difference in the mean error, where the reconstruction error is a lot lower on an average scale of about 0.5, which means that after maintenance, there definitely is an improvement where there's much less anomalous data gathered. So I'm going to close this. Now let's see what the test accuracy is of the autoencoder network, as well as let's also place crosses on what it takes as anomalous data that it has evaluated. So we'll do that quickly. And we'll be setting a threshold of about 0.5. So when the reconstruction error for each specific data point is higher than 0.5, then that will indicate that it is classed as anomalous. And you can see this over here as well. I'm just going to enlarge this. With the confusion matrix on the right, we can also see that it performed relatively well for the predicted class versus true class. And for the reconstruction error graph over here, we can see a test accuracy of about 94.1%, which is quite good. And we can also see for the number of observations that we are looking at that there is quite a bit of anomalous data that has been detected. And so, yeah, for the conclusion of this demo, 3 different models have been used to detect anomalies, with the one class SVM having the best performance of about 99.7% for detecting anomalies within the test data. The relative performance of this can change. Remember, if you select different features that we've selected in the Diagnostic Feature Designer app, you can have different results, or if you select different hyperparameters as well for each model that you use. So you guys can go ahead get started with the Diagnostic Feature Designer app and further experiment with the feature selection, run it through a model, and then see what results you guys get. Okay. Oops. Okay. To close off this webinar, let's go through a recap of what we did. Now, we went through anomaly detection, as well as we looked at how difficult they can be to identify. We looked at the types of equipment maintenance that you can do, which are reactive, scheduled, as well as predictive maintenance. We looked at a typical predictive maintenance workflow. We've got a model that you train, data that you collect, you process that data, as well as you can deploy that model as well. We've also gone through a case study on condition monitoring of substation equipment using thermal cameras. We've gone through a demo on developing an algorithm for vibrational analysis. And I also would like to, as we close off, I'd also like to point you guys to previous webinars that have been conducted, which is called a Taught a Machine to See Anomaly Detection in Industry, delivered on the 16th of August by my colleague Varushan Kapoor, as well as Uncovering the Unseen Event Detection through Computer Vision, delivered on the 30th of August by another colleague of mine, Doron Joff. You guys can go ahead and watch those webinars. This will be the conclusion of this will be the final part of this computer vision webinar series. And now, with the content all wrapped up, this is an opportunity for you guys to ask questions. Are there any questions? Any questions at all? Anything, anyone? Okay, cool. So thanks, Opti-Num team, as I see you guys, for attending. You can follow us on our LinkedIn as well as Instagram at Opti-Num Solutions. You can also visit www.optinum.co.za for more information, as well as contacting each of the presenters for this 3-part computer vision webinar series on their emails. This pack of slides will be shared with you guys. I hope you guys have a great day. Thanks for attending.
Thanks, Enzo. Well done.
Thanks so much.